Well, we had our discussion on atomic size and related it to both neutral atoms and ions. And today we are going to look at ionization energy. What's the trend in ionization energy? We'll talk a bit about why that is. But when we talk about ionization energy, we are talking about the amount of energy required to remove an electron from the ground state of a gaseous atom or ion. So when we collect that value, when we determine that value experimentally, that's how we find it. But for the basic understanding, it's the amount of energy required to remove an electron from the ground state from a substance. We'll look at the first ionization energy, and that's the amount of energy to remove the first electron. And then you can have things like second ionization energy and third, and that's to remove additional electrons, but in a particular order. So with this graphic that's in your textbook, which you should glance at as well, but you'll notice that there is a trend. So in this table, you've got a variety of columns. The first column is for the first ionization energy. Second column is second ionization energy, and then third, fourth, fifth, sixth, seventh. Okay, you get the idea. So it requires more energy to remove each successive electron. So it takes more energy to remove the second electron, even more to remove the third and fourth. And some atoms, it's very difficult to remove an additional electron. So if you think of sodium, sodium has 11 electrons. 2 electrons in the first energy level, 8 in the second energy level, and 1 in the third energy level. So for sodium, the first ionization energy is 495. Okay? But you notice if we try to remove another electron, so the second ionization energy, it is a significant amount of energy to remove one more electron. And that's because you're trying to remove an electron out of the inner shell of electrons, or the inner core of electrons, which takes a lot more energy than removing an electron that's in the outer shell, or the most outer shell of an atom. And you can kind of see that trend as we go along. And keep in mind this group of elements is going across the third period, so sodium, magnesium, kind of going all the way across. And you notice how that ionization energy to remove a core electron is significantly higher than to remove an additional, a third or fourth or a fifth electron. So this leads to the statement of when all the valence electrons have been removed, the ionization energy takes a significant jump from where the amount of energy it took to remove those valence electrons. So the outer electrons, easier to remove those electrons. And you notice as we get closer to the noble gas side, okay, to remove all the electrons to have just the inner core, it takes a lot of energy. And that's why typically sodium, magnesium, and aluminum are going to lose electrons, because the ionization energy needed to remove those electrons it gets high for aluminum, but it's nothing compared to, if you look at like chlorine or sulfur, to remove 6 or 7 electrons. It's going to take a lot if you want to try to go that way to make a full shell. So when we look at the trends in the periodic table, kind of using this 3D graph, you'll notice that the lowest energy area for ionization energy is down in the bottom left corner. So it takes the least amount of energy to remove the first electron from the bottom right, and it takes the most amount of energy to remove the first electron from the top right. Okay, so bottom left, top right, that is the trend when looking at the periodic table. So then another way to look at it graphically, so as you go across a row, it gets harder to remove an electron. As you go from left to right, the Z effect, or the nuclear effect, increases because you're gaining electrons. So you're gaining electrons as you go from left or sorry, you're gaining electrons and protons as you're going from left to right. So there's more protons pulling in those electrons, but there's no additional shielding as you go from left to right, or it's very minimal. So we kind of talked about that in class, where the electrons that are within the same shell that you're discussing only contribute about 3.35 to the shielding effect. So then there are some discontinuities in this trend. So you'll notice the circled areas that are on this slide. So a variety of circled areas that seem to kind of mess up the trend. So let's talk about those. So the first occurs between groups 2A and 3A. So I would love it if you pulled out a periodic table and kind of looked at where those are. So you're jumping from lithium. So let's look at this kind of second set here. So we're at lithium down at the bottom and near kind of 500. It jumps up to, I don't know, whatever that is, 900. But it jumps, so that is, so we go lithium, so that's beryllium. Then it drops back down to, that's going to be boron. Okay, and then it starts climbing up again, goes up, and then you get to nitrogen, then it drops down to oxygen, then fluorine, then neon. Okay, so in these little dips, you have orbitals, like suborbitals, that are either full or becoming partially full or half full. So like where you go from beryllium to boron, the boron is, or the beryllium, the s subshell is completely full at that point. And so when you have one electron in the p and two in the s, removing that one little p makes it so that the whole s shell is full and there's no extras in the p. So it takes a little less energy to remove that one little p electron. And then the same thing with the bump as we go up will occur as well. So electron is removed from a p orbital rather than an s orbital. The electron removed is farther from the nucleus. There's also a small amount of repulsion by the s electrons. So then for this other grouping that I was kind of jumping ahead and starting to talk about, is that you have all the p orbitals filled with single electrons. And then when you go back to fill in the orbitals with an additional electron, you have more repulsion because you're rather than the electrons being able to spread out, they're kind of filling all these spots, and so that kind of assists in the removal of that one electron that's added as you go back to backfill the p's. Okay, so we will continue our discussion on this in class, but please, if you would just review this section 7.4 in your textbook as well, so that it's not just the slides, but you're also looking at the textbook as well. We'll see you in class. Bye-bye.